The goal of this course is to help you write SQL statements and data access code that run faster and are more efficient. To do so, we need to ask ourselves, what are the types of performance metrics that we should look at while we are tuning our applications so that we can objectively know that we are improving performance? The first performance metric to discuss is the performance metric that most people are most familiar with, and that is elapsed time. Elapsed time is simply the amount of time that a SQL statement took to execute. Elapsed time is an important metric because this is how our end users think of performance. They will say to us that a certain web page needs to be able to load in 3 seconds or less, or that a report they're trying to run is taking 20 minutes, and that's too long. And to the surprise of no one, it's always our goal to minimize the amount of elapsed time that a SQL statement, or indeed any operation, takes. Think about it. When was the last time one of your users asked you if you could make something run slower? When we are tuning SQL statements, though, while minimizing the amount of time a statement takes as our end goal, there are other metrics that turn out to be more useful. And the reason for this is that the amount of elapsed time that a statement takes is really a product of a number of other performance metrics and factors. That is, elapsed time tells you the final result, but it doesn't tell you why the operation took that long. So we need to be able to look at other performance metrics to figure out what is driving performance. Secondly, we have to be careful when we're looking at elapsed time results, as they can be impacted by a number of external factors that are beyond your control as an application developer. For example, how long a statement takes is dependent on how busy the database server is when a statement is run. If a statement is run during peak load or while a database backup is being taken, then the statement is naturally going to take longer. But this isn't in response to anything that we're doing in our application code or anything that we have control over. So we want to look at elapsed time as an end result, but for actually understanding what is driving the performance of the SQL statement, we want to dig deeper and look at other metrics. Probably the best metric to look at for judging statement performance is the number of logical I/Os that a statement performs. Quite simply, the number of logical I/O operations is the number of read operations that a SQL statement performs from the Oracle buffer cache. If the buffer cache does not contain the data that the SQL statement needs, then there will also be an associated physical I/O operation for the statement. But no matter what, when Oracle needs a block of data, a logical I/O will occur. So in this way, the number of logical I/Os give you a good indication of how much data Oracle is having to process in order to execute your SQL statement. The amount of data Oracle has to process in order to complete your SQL statement will affect the performance of the statement in a number of ways. First of all, if you have a high number of logical reads, it is highly likely that a significant portion of the data blocks that your statement needs won't be in the buffer cache. And therefore, Oracle will have to go to disk and read this data off of disk. As we all know, reading data from disk is much slower than reading data from memory, especially a large amount of data. Second, Oracle is going to have to process the data for all of those blocks. This could be filtering the data to look for only the rows of interest, joining the data to another data set, or sorting the data. But regardless, this is going to take both time and CPU to perform these operations. Intuitively, we know that any time we have to process a larger data set, no matter what technology it is that we are using, this is going to take longer and use more resources. And this same principle is true in Oracle. The other fact to consider when evaluating the number of logical I/Os a statement is having to perform is the fact that this is a consistent metric. That is, if you run the statement over and over again, you're going to get the same number. And this number isn't going to be affected by things like other users on the system or what data happens to be in the buffer cache at that moment. And so when you start tuning a SQL statement and you see a change in the number of logical I/Os performed, you know that this change in the number of logical I/Os is in response to the change that you made in your tuning efforts and not in response to some external event. And in performance tuning, this is very important. Historically, Oracle has used the term consistent gets rather than logical I/Os to refer to the operation of reading a data block from the buffer cache. Recently, however, Oracle has started to use the term logical I/Os more often, and the term logical I/Os is a little bit more standard across different database platforms, so that is the term that I'll be using in this course. Just know that when you do read the Oracle documentation or see the term consistent gets used in some of the Oracle tools or statistics, this is just another term for logical I/Os, so don't be confused by that. So how do we see the number of logical I/Os that a statement is performing? There are a couple of ways that Oracle makes this data available to us. First, in tools like SQL Plus and SQL Developer, we can use the autotrace command to execute a statement and get a detailed performance report, and included in this report are the number of logical I/Os. In fact, in SQL Developer, we'll even get a breakdown of the number of logical I/Os by operation performed in the execution plan, so we can target what specific operations are reading and processing the most data. All of this is demonstrated in detail in the module in this course on statement level performance tuning. Every time Oracle executes a statement, Oracle will also keep detailed statistics of the execution of that statement. And these statistics are summarized and available to you in a series of views known as the $$ views. Most notable for us is the $$ SQL Stats view. By querying data from this view, we can easily see what statements in the database are performing the most logical I/Os on average, and then target these statements for performance tuning. We can also see other statistics like the average amount of CPU time used, the average elapsed time a statement took, and the number of times a statement has been executed. How to query this information out of the $$ SQL Stats view and other related views is covered in the module named Monitoring Oracle Applications. In either case, we'll be able to get a good read on how much data a statement is processing, and then target the correct statements for performance tuning based on this data. Let's take a moment to talk about how CPU is used by SQL statements and Oracle in general. Oracle servers handle a large volume of requests, so it is not unusual to see 80 or even 90% of the CPU being consumed on the database server at any time. Of course, if the amount of CPU used on the server goes to 100%, then most likely we have some processes that need CPU resources but aren't able to get it, so these processes will have to wait until CPU becomes available. And so like any other resource, we want to make sure that we are using CPU as effectively and efficiently as possible, so we aren't introducing unnecessary bottlenecks into our system. There are two main areas where a SQL statement uses CPU resources. The first of these areas is in parsing the SQL statement. Every SQL statement submitted to Oracle must be parsed and have an execution plan created. And as it turns out, this is a CPU-intensive process. There are also some implications around getting access to the shared SQL area that if you aren't using bind variables correctly, you will encounter latching issues on your Oracle server, and this will cause a lot of CPU resources to be wasted on the database server. In the module on bind variables, this is discussed extensively, but in short, you want to make sure that you're always using bind variables in your application, otherwise you're going to be wasting a lot of CPU resources. The second area where CPU is used is the actual processing of queries. Every time Oracle has to perform a comparison, a join operation, or sort a data set, this takes CPU. The more data that is involved in each of these operations, the more CPU will have to be expended in order to complete the operation. So here again, we look at both the amount of CPU being used, but also at the number of logical reads, because if we can reduce the size of the data being operated on, we'll save CPU. To wrap up this discussion of performance metrics, while our ultimate goal is to reduce the amount of elapsed time it takes for each statement to run, what we really want to do is look at other performance metrics in order to guide our tuning efforts. When we look at other metrics, like the number of logical I/Os a statement is performing, they are really helping us understand how efficient the statement is. If a statement is having to read and process a lot of data, this statement is going to have to perform a larger number of physical I/O operations and use more CPU, all of which will take more time. If all of the data is needed in the final result set, that is okay, and that might be the best that you can do for that statement. But if Oracle is having to read and process through a bunch of data that ultimately won't be used, this is wasteful and inefficient. It is inefficient in the fact that this extra work will make your SQL statement take longer and force your user to wait. And it is inefficient because it is consuming additional resources on the Oracle database server. So this might cause a performance bottleneck that causes other statements to run slower than they should in your application. And so, as you start to think about performance tuning, you want to start to think in terms of statement efficiency rather than purely how long a statement takes to execute, as it is statements that are efficient and only use the minimum amount of data that they need that deliver the best performance.